So I'm at the top of page 15 to do our first example. So for these directions, we're asked to find the interval of convergence for the series. For what values of x does the series converge absolutely? And for what values does the series converge conditionally? This is non-alternating, so we don't have to worry about Leibniz's theorem for this one. So like we said before, to find the IOC, we're going to run the ratio test. And as you remember, I told you the ratio test is your friend. So we're going to take the limit as n goes to infinity of the absolute value of a to the n plus 1 over a sub n. So anywhere there's an n, replace each and every n with n plus 1. So that's going to give us n plus 1 factorial x minus 4 to the n plus 1 all over n factorial x minus 4 to the n. So now we're going to play around with our rules of exponents, and I know that if I simplify this expression, I'm left with x minus 4, and if I simplify these factorials, I'm left with n plus 1. So just like we did before, anything inside of our expression that does not involve an n, you move it to the front. So I have x minus 4 times the limit as n goes to infinity of the absolute value of n plus 1. Okay, so if we take this limit, we see that this limit is going to go to infinity, but we're multiplying it also by x minus 4. I need this to be less than 1 for convergence by the ratio test. There is only one value of x that I can pick that'll make this times infinity less than 1, and that is when x is 4. So the only way for L to be less than 1 is if x is equal to 4. Because then we'll have 4 minus 4 times infinity, which is 0, times infinity, which is 0, is less than 1. So what we say here is that we converge absolutely. I'm going to abbreviate converge absolutely like this, at x equals 4. Converge conditionally, nowhere. This will make more sense once you see some examples where we're actually conditionally convergent. Okay, let's move on to the next problem. It's rather long. Find the interval of convergence, so that's going to tell us to run the ratio test. It's non-alternating. For what values of x does the series converge absolutely, and for what values of x does the series converge conditionally? Directions are the same for every problem. So we're going to run the ratio test. The limit of the absolute value of a to the n plus 1 all over a to the n. So I'm going to write n plus 1 in for n everywhere, so this becomes x to the n plus 1 all over 3 to the n plus 1. Watch out here. N plus 1 square root of n plus 1 all over x to the n, 3 to the n, n square roots of n. I'm going to go ahead and use some of my rules of exponents to simplify before I try to evaluate the limit. So let's flip the guy so we can get this into a form that'll allow us to simplify. 3 to the n plus 1, and I'm going to rewrite this as n plus 1 to the 3 halves. And that's being multiplied by 3 to the n. This I will rewrite as n to the 3 halves all over x to the n. Okay, so now we're going to be doing lots of work here. This and this will simplify, and all that's left is an x. This and this will simplify, all that's left is a 3. This and this are over the same power. So actually this is going to be to the 3/2 power n plus 1. So just like we said before, anything not involving n can be moved out front of the limit. So I'm going to rewrite this as the absolute value of x over 3 is equal to the limit of n over n plus 1 to the 3/2. Now let's evaluate the limit, and remember that we will converge. We want to force this out to be less than 1 for convergence. Now I can't necessarily apply L'Hopital. I am going to get infinity over infinity, but here's a case where we're just rationalizing our answer. If n is 1,000,000, so the numerator is going to be 1,000,000, the denominator is going to be 1,000,000 plus 1. And if I take that ratio and take it to the 3/2 power, this is basically going to go to 1. So I have the absolute value of x over 3 times 1 less than 0, or it's this inequality that we will have to solve. So let's remove the absolute value and let's get x by itself. So this is our interval of convergence. We will converge absolutely between -3 and 3, but what about the endpoints? So we have to test the endpoints to see if we converge there. So this is where you really want to be paying attention, because this is the first time I'm doing this. So I want to test the endpoint at x equals 3. So I'm going to go back to my original, and I'm going to plug a 3 in for x right there. So my series becomes n equals 1 to infinity, 3 to the n, all over 3 to the n to the 3/2. And something nice happens, doesn't it? This cancels this. So all I'm left to evaluate is this series. And if I do a careful study of what I'm given, I see that this is the p-series test. And I know that since that's bigger than 1, we converge. So we converge by the p-series. So since we converge by the p-series at 3, then I know that 3 is included as an endpoint because we converged there. So now we have to continue on and test the endpoint at x equals -3. This one's going to be a little more challenging. Okay, same idea. We're plugging in the -3 in for this x value. So this becomes -3 to the n all over 3 to the n to the 3/2. Here we go. Can't see. Okay. Now I see that we have a negative here, so that's going to force this to alternate in sign. So I'm actually going to bring that and isolate that term. Once I do that, again something nice happens. This cancels this. So the series that I'm left to evaluate is -1 to the n over n to the 3/2. So this is an alternating series, so I have to use Leibniz's theorem. So I'm going to write 1, 2, 3, and my use of n is going to be 1 over n to the 3/2. And if I write out a few terms, I should be able to see, I should be comfortable with the idea that this is going to be decreasing as n grows. So use of n is always positive. Use of n is greater than use of n plus 1. And if check, if I take the limit of 1 over n to the 3/2 as n goes to infinity, that is equal to 0. So by Leibniz, we converge. So check for a mismatch. So we know that 1 over n to the 3 halves converges by the p series.